Okay, so ladies and gentlemen, this calibration model is one that you should have seen introduced by me in a video that you would have watched last week. And within this model, we are trying to match some historic data using output from a model. That's the idea of calibration. Often, there's some data you have that can go into specific parameter estimates, and then there's some data which doesn't relate to a particular parameter in isolation, but it kind of constrains your understanding of how the model should behave as a whole, the emergent behavior of the model. And for that sort of data, that sort of empirical data, you can't just get an estimate out, put it into parameters. Instead, you're trying to match the model output, on the one hand, the model output with this data. So here's an example time series. And we're taking a model that lies behind here, this model here where we have people getting infected and infect each other. And you're adjusting the parameter values so that the model output comes as close as possible to this empirical data. And one of the challenges of this that you should have learned via the video is the fact that with an age-based model, there's stochastics involved. So a given run with specific sets of parameters may yield different results for different realizations. Sometimes it may give closer results, sometimes further. And you don't want to just run the model once with a given set of parameters if it's stochastic, because by fluke it might perfectly match the empirical data, or very close, but it was just a fluke of the circumstance, of just the luck of the draw. And if you ran it again, same parameters might yield very different results. So here, it's adjusting again and again with the same set of parameters. It might run the model many times. And the basic mechanisms for this, ladies and gentlemen, are illustrated here in the model. And there's very similar mechanisms to what you used in your parameter variation. So there's some work to set the experiment up, to initialize the historic data, and sort of clearing out some information. And then every time the model runs, every single realization of the model for each different random number seed, it's taking what comes out of the model and storing it away in the experiment. Because the model itself, main, is going to disappear. It's going to be destroyed, because it runs main maybe 100 times or 500 times. Each time it reads this information out after main is done running, and it puts it into this place here. Now, by virtue of putting it in there, it is going to then allow it. Note this DS infectious current. That's where it got that data. The historic data it got at the very start of the model, the very start of the experiment, from some table function. And every single realization, it's going to do a comparison between the historic data, in other words, the observed data, and the model's output. And that's going to be, that the result of this is going to be a measure of how discrepant they are, how different they are. So if they exactly match, difference is going to return 0. If they're really different, it's going to return a large value. And it's always going to return a value that's 0 or higher. Okay. And as a result, it's going to be trying to minimize this objective. You see, it says minimize this, to try to make it as small as possible. In other words, try to match it as closely as possible. Okay? And you see it's trying and getting varied results in terms of the match. This indicates the discrepancy of its best match from what it actually achieved. And that discrepancy is going down. The red line indicates it's getting better and better. These different little gray blocks indicate it's trying and trying and trying again with very varied results. But over time, it's kind of learning a little bit what's going on better. Now, this objective function is going to be critical for your assignment 4, because you're going to be taking into account not just one time series, but several. Okay? A few observations. Number one, this is where you measure the difference between one time series and another. Number two, it can never be negative. Meaning, if you have a discrepancy with respect to one, the other one can't be negative, so it cancels out some of that discrepancy. It can only be 0 or more. And you need to have a way of combining the discrepancies with respect to one and with respect to another so that you get an overall discrepancy. Okay. This specifies the number of iterations that you'll be running. Now, beyond this, there's a choice here as to the number of replications you want to run. Okay, and these replications indicate, okay, for each particular assumption about parameters, that, you know, this parameter here equals contact rate equals 0.5, infection probability equals 0.1. For that particular assumption, for example, it's going to run it 5 times. And here, of those parameters, of these parameters over these ranges, it's going to be running it 5 times because of stochastics, because each time it may give a little bit of different results, and it doesn't want to make its recommendations the best parameters contingent on the luck of the draw. So it's running a bunch of times, and it averages together those outcomes to find sort of the average of the discrepancy function, the average of the so-called objective function for those sets of parameters. Okay, so in that assignment, you're going to be introducing some new data, etc. And just be aware that a lot of the elements are here. You're just going to be tinkering around the edges with them. For example, that historic data that it's using right now it's being put into a data set in the experiment, but it is actually, here, if we go look at here in the calibration, there's a thing called infectious historic. And this infectious historic, this is actually the time series. Okay, so we'll go there, come on. There it is, over to the left. And this is actually a time series, so it's data over time. Hey, come on. There's time, 2, 4, 6, 8, etc. And this is the number of people infected at each of those times. And so this is what it looks like. Each of these points corresponds to a particular row here. Okay? And so you're going to need to create a similar time series for yours, for the other data set that you're going to be reflecting. And just to sort of bring the circle round, note this infectious historic. That's the table function. This is what's called a data set. It can hold values or pairs of values, okay? In this case, it's holding pairs of values, a horizontal and vertical, X and Y, you can think of them. And at the beginning of the calibration experiment, it is going to fill up that data set right here with those pairs. It's going to fill up those pairs from that table function we just looked at, this table function of data over time. And you're going to go through and do a very similar thing for yours. Okay? So just be aware these are the pieces. This mechanism right here, where basically it's looking for the best iteration and remembering the one that was best, that's a fine thing. You don't have to worry about this much, but this is used for its animation. So you actually will not have to specifically change that, but this is actually sort of remembering the best results. And if you want to do that for your other time series, the other data that you'll be dealing with, you'll have a second DS infectious best and DS new cases best or something like that. Okay? So that's kind of how this simulation works. That's how calibration works. And you're going to be tinkering around the edges of this experiment that you see here to make it easier for you. It's going to be provide a framework. Any questions about that? I'm keenly aware that your final weeks are high pressure, and I just want to make sure that you have all the tools at your disposal to undertake the final assignment. Questions right now? Yeah.
That difference function, how does it work? It just
Yeah.
it's the difference between every piece of data at a specific time.
No, so great question, Alex. So difference here, it's actually taking in, there's actually a bunch of overloaded versions of it, two of them here. One is to compare a data set with a data set, and that's what we're doing. And you'll notice that it says that it returns the square root of the average of the squared difference between linearly interpolated data sets, okay? The integration range is the intersection of the argument range of the data set. Now that's a fancy term, but what it's going to be doing is it's here if we have one time series. Oh, maybe. Let's continue over there. Here we go. You folks on this side of the room shouldn't be penalized because of a bad marker. Okay, there we go. Great. And suppose this is the historic data, and the output from the model looks something like this. Okay. Mm-hmm. So the simulation, given the structure of the simulation and the particular parameter values being assumed right now, it outputs something like that. That's kind of your theory of the world. And you're asking how far off is that from this guy? Well, what this is going to return is you're going to be giving it this on two data sets. So these data sets are each going to be a time series. It's going to be, one is going to be a time series associated with this guy here. There's going to be data points here for the historic. Okay, they're going to appear in that, remember that table function we saw a short time ago? It's going to specify a time 0, it's whatever, time 2, it's whatever time.
So it's going to take
4.
a difference between the intervals.
Yeah.
The integrals between two intervals.
So that's right. So what it's going to be finding out here is, oh man, keep pointing that camera at me. Okay. So it's going to be here comparing the data, the numbers coming out of the model with this, okay? And it says linearly interpolated because suppose one has a data point at a time that isn't represented in the other. Mm-hmm. Then it will figure out, okay, what would that value probably be close to by interpolating between those that it does have. But basically, it's going to take, in this case, because actually it could be recording at the same times it has, it's going to be taking, for each of these time points where it has a data point, it's going to take the difference between them, one minus the other, and it's going to square it. Because it's a square, it doesn't matter whether it's A minus B or B minus A. One is the negative of the other, the square of them, by squaring each of them, it's the same number. So it's going to be taking, for each point, the square of the difference between these, and then it's going to be averaging that over the entire time and taking the square root. Okay? So this is very similar to, it's kind of a variant of what's called the sum squared, or the square root of the sum squared error. So it's like, it's something along the lines of, x, this is the model output minus y, that's the observation, squared plus, x1 minus y1 squared, plus all the way to the last one, call it x, time, it's at time n, so it's xn minus yn squared. And it says it's averaging them, so it's putting this all over, oh man, I should have, I'm a computer scientist, not a mathematician, so it'll be n of them, so it'll be over n, okay? One of the things you'll find is computer scientists like to go from 0 to n minus 1, and mathematicians like to go from 1 to n. And there's a little bit of a tension there, like when we're on each other's theses committees. We like our zeros in computer science. Imagine doing programming without zeros, that'd be pretty bad. I once heard the Roman Empire fell because of a null point error. That's not true. Okay, so in any case, this is what that's computing. Is that helpful? Yeah. Okay. And it wasn't because they had no zeros either. Okay, so so that's what that means. Other question though? Okay, question back there, the last row. No? Okay. So, ladies and gentlemen, this is going to be the difference between model output and empirical data for one set of data, and you're going to do a very similar thing for the other data. This is a built-in function difference. You just have to pack up your data in these data sets, and that's exactly what's going on in this little code that we looked at here. That's exactly what's going on here. Is you're getting the data from the historic into this data set, and you're getting the data from main before main disappears, before it's deep 6, before it vamooshes. You're extracting it and you're putting it into this data set, okay? And that's what allows you to compare the two. These data sets were filled in, so you can take the difference between the two, and you'll do something very similar for your others, or for the other one, okay? And generally speaking, if you want to consider the difference in one is similar to the difference in the other, you'll add them together, okay? Okay. Questions? That should put you in good stead for that problem. The flocking one, you should see flocking, you should see swooping behavior, etc. There should be sort of obvious behavior of the so-called birds together. They should look like fish or birds in the sense that they swoop around, etc. So that will take a little bit of work just to sort of characterize that at the basis of the rules that have been given. Okay. You will need the Apache Commons math library, which I've provided to you for that problem. For this problem, you will need some data, which I've also provided for you on the Moodle site, together with the assignment. Okay? Hopefully that should put you in good stead to finish that up without too much extra work on the top of your term. Okay? Other things? Okay, great. So that closes my remarks on the assignment 4. Naturally, I'll be glad to answer questions about that over the next few weeks in my office hours.